Introduction. Students, do you know what integers are? A whole number that can be positive, negative or zero. Correct. And what are whole numbers? The set of numbers that include 0 plus the set of natural numbers. Good. Today we will learn about real numbers. Real numbers consist of rational and irrational numbers. Real number system has many subsets: integers, natural numbers and whole numbers. Come, let's study real numbers in detail. Objectives. At the end of this lesson, you'll be able to explain Euclid's division lemma, explain the fundamental theorem of arithmetic, solve questions by using prime factorization method. Euclid's division lemma. Euclid's division lemma states that for any two positive integers a and b, there exists unique integers q and r such that a is equal to bq plus r. 0 is smaller than or equal to r, which is smaller than b. For example, a is equal to 15, b is equal to 3. It is observed that 15 is equal to 3 into 5 plus 0, where q is equal to 5 and r is equal to 0. Lemma. A lemma is a proven statement used for proving another statement. An algorithm is a series of well-defined steps which gives a procedure for solving a type of problem. Euclid division algorithm can be used to find the SCF of two numbers. It can also be used to find some common properties of numbers. How to obtain HCF? To obtain the HCF of two positive integers, say c and d, with c is greater than d, we have to follow the steps below. Step 1. Apply Euclid's division lemma to c and d. So, we find whole numbers q and r such that c is equal to dq plus r. Step 2. If r is equal to 0, d is the HCF of c and d. If r is not equal to 0, apply the division lemma to d and r. Step 3. Continue the process till the remainder is 0. The divisor at this stage will be the required HCF. Example of HCF calculation. Let us find the HCF of 455 and 42 using Euclid's algorithm. Solution. Since 455 is greater than 42, we apply division lemma to 455 and 42 to get 455 is equal to 42 into 10 plus 35. Remainder is not 0, therefore we apply lemma to 42 and 35. 42 is equal to 35 into 1 plus 7. Again, the remainder is not 0, therefore we apply lemma to 35 and 7. 35 is equal to 7 into 5 plus 0. We can see that the remainder has become 0 and we cannot proceed any further. Therefore, the SCF of 455 and 42 is the divisor at this stage. Example of Euclid theorem. Let us now prove that every positive even integer is of the form 2q and that every positive odd integer is of the form 2q plus 1, where q is some integer. Solution. Let a be any positive integer and b is equal to 2. Then by Euclid's division lemma, there exist integers q and r such that a is equal to 2q plus r, where 0 is smaller than or equal to r is smaller than 2. Now, 0 is smaller than or equal to r is smaller than 2, which implies 0 is smaller than or equal to r is smaller than or equal to 1, which implies r is equal to 0 or r is equal to 1 because r is an integer. Therefore, a is equal to 2q or a is equal to 2q plus 1. If a is equal to 2q, then a is an even integer. We know that a positive integer can be either even or odd. Therefore, any positive odd integer is of the form 2q plus 1. The fundamental theorem of arithmetic. The basic idea is that any integer above 1 is either a prime number or can be made by multiplying prime numbers together like this. Let us start with the definition. Any integer greater than 1 is either a prime number or can be written as a unique product of prime numbers, ignoring the order. Look at these numbers. Relationship between LCM and HCF. For any two positive integers a and b, HCF AB into LCM AB is equal to a into b. Example: if a is equal to 3 and b is equal to 6, HCF 36 into LCM 36 is equal to 3 into 6 equals 18. This result can be used to find the LCM of two positive integers if we have already found the HCF of the two positive integers. We can find that HCF and LCM of the two numbers with the help of the prime factor. Let us see how. Find the LCM and HCF of 510 and 276. 510 is equal to 2 into 3 into 5 into 17. 276 is equal to 2 into 2 into 3 into 23. The common factors of 510 and 276 are 2 and 3. Thus, the HCF is equal to 2 into 3. For finding LCM, write common factors once and then write remaining prime factors of each number, then multiply all these and you will get LCM of the given number. 510 is equal to 2 into 3 into 5 into 17. 276 is equal to 2 into 2 into 3 into 23. The common factors are 2 and 3 and the remaining prime factors of 510 are 5 into 17 and remaining prime factors of 276 are 2 into 23. Thus, LCM of 510 and 276 is equal to 2 into 3 into 5 into 17 into 2 into 23 equals 23,460. Let us see what is the relation between the product of LCM and HCF of the two numbers and the product of two numbers themselves. From the above discussed example, product number is equal to 510 into 276, which equals 1,40,760. Product of HCF and LCM is equal to 23,460 into 6, which is 1,40,760. Thus, product of HCF and LCM is equal to product of numbers. More accurately, for two given numbers a and b, HCF AB into LCM AB is equal to a into b. Example: the LCM of two numbers is 126. If one number is 18 and HCF of the numbers is 2, find the other number. We know that product of two numbers is equal to product of the LCM and HCF. That is, 18 into x is equal to 126 into 2. Here, x is the other number. That is, x is equal to 126 into 2 upon 18. That is, x is equal to 14. Examples of fundamental theorem of arithmetic. Given that HCF 306, 657 is equal to 9, find LCM 306, 657. Solution. We know that the product of HCF and LCM of two numbers is equal to the product of the given numbers. Therefore, HCF 306, 657 into LCM 306, 657 is equal to 306, 657 is equal to 9 into LCM 306, 657 equals 306, 657, which is equal to LCM 306, 657 equals 306 657 upon 9. LCM is equal to 22,338. Did you know? In the 17th century, Descartes introduced the term real to describe roots of polynomial, distinguishing them from imaginary ones. Carl Friedrich Gauss is often referred to as the Prince of Mathematicians and is considered one of the three greatest mathematicians of all time, along with Archimedes and Newton. He has made fundamental contributions to both mathematics and science. Summary. Let us summarize what we have learned. Euclid's division lemma. Given positive integers a and b, there exist whole numbers q and r satisfying a as bq plus r, 0 is smaller than or equal to r is smaller than b. Euclid's division algorithm. This is based on Euclid's division lemma. According to this, the SCF of any two positive integers a and b, with a is greater than b, is obtained as follows. 1. Apply the division lemma to find q and r, where a is equal to bq plus r, 0 is smaller than or equal to r, which is smaller than b. 2. If r is equal to 0, the SCF is b. If r is not equal to 0, apply Euclid's lemma to b and r. 3. Continue the process till the remainder is 0. The divisor at this stage will be HCF AB. Also, HCF AB is equal to HCF BR. The fundamental theorem of arithmetic. Every composite number can be expressed factorized as a product of primes, and this factorization is unique apart from the other in which the prime factors occur.